group number 4, B4, B1B. This exercise 5 memory hierarchy. Exercise 1. To calculate the average access time, we need to consider both cache hit and cache miss. Given memory cache access time, cache hit time for ns, memory access time 80 ns, time to load a line in cache 120 ns, hit radius 95%, read operation 90%. We can calculate average access time as follows. Average time access time equal to hit time minus hit radius plus miss time multiplied by miss radius. Calculate the hit time. Hit time equal to memory cache access time equal to 4 ns. Calculate the miss time. Miss time equal to memory cache access time equal plus time to load a line in cache equal to 4 ns plus 120 ns equal to 124 ns. Calculate the miss radius. The miss radius equal to 1 minus hit radius ratio equal to 1 minus 0.95 equal to 0.05. Calculate the read miss radius ratio. We read miss ratio equal to miss ratio multiplied by read operation ratio equal to 0.05 multiplied by 0.9 equal to 0.045. Calculate the average access time. Average access time equal to hit time multiplied by hit radius ratio plus miss time multiplied by miss ratio equal to 4 ns. 4 ns multiplied by 0.95 plus 124 multiplied by 0.05 equal to 10 ns. So the average access time for the computer is 10 ns. Exercise 2, part A. To determine the number of bits index and offset, we need to consider the block size in the number of blocks in the cache and set associativity given. Block size 64 bytes, number of blocks in cache 128, set associativity 4-way. Total number of sets in the cache can be calculated by dividing the number of blocks by associativity by 128 divided by 4 equal to 32 sets. To determine the number of bits in the index, we need to find the number of bits required to represent the set number size. There are 22 sets. We need 5 bits to represent the index. 2 power of 5 equal to 22. The offset is determined by the block size. The block size is 64 bytes. We need 6 bits to represent the offset. 2 power of 6 equal to 64. The remaining bits in the address are used for the tag. Size the address is 32 bits. In total, we have 5 bits for the index and 6 bits for the offset. The number of bits for the tag can be calculated as 32 minus 5 minus 6 equal to 21 bit. Therefore, the number of bits is in the tag is 21 bit. The number of bits in the index is 5 bit, and the number of bits in the offset is 6 bit. Exercise part B. To calculate the total cache size in bit, we need to consider the size of each block and total number of blocks in the cache given. Block size is 64 bytes. Number of blocks in the cache is 128. The total cache size can be calculated as follows. The total cache size equal to block size multiplied by number of blocks equal to 64 multiplied by 128 equal to 8192. Size the x bit require 8 bit. We can convert the cache size to bit. So total cache size in bit equal to total cache size multiplied by 8 equal to 8192 bit multiplied by 8 equal to 65,536 bit. So the total cache size is 65,536 bit. Exercise 3. To calculate the hit ratio, we need to obtain an average access time of 20 ns. We need to consider the cache memory access time and the main memory access time. Let's assume the hit ratio is denoted by h, and the miss time is 1 minus h is denoted by m. Given cache access time equal to 10 ns, main memory access time equal to 120 ns, average access time equal to 20 ns. The average access time can be calculated using the following formula. Average access time equal to cache access time minus by hit time multiplied by hit time plus main memory access time multiplied by hit time. Hit time equal to time to access data from the cache. Miss time equal to time to access data from the main memory. We can rearrange the formula to solve for the hit ratio. 20 ns equal to 10 ns multiplied by h plus 120 ns multiplied by 1 minus h. So the equation is so the result is h is about 1.909. So to achieve the average access time of 20 ns, the hit ratio of approximately 0.909 or 90.9% is needed. Exercise 4, Part A. The memory cache has the size of 256 kilobytes and the cache line size is 64 bytes. To calculate the number of lines, we divide the memory size by the cache line size. Number of lines equal to memory size divided by cache line size is equal to 256 divided by 64 is equal to 4096. Since the cache is four-way associative, we divide the number of line by the number of way to get the number of set. Number of set equal to number of line divided by number of way. 4000 4096 line divided by 4 ways. We have 1024 set. Therefore, the memory cache has 4096 line and 1024 set. Exercise for part B in C. B, the block size transfers between the cache memory and the main memory is equal to cache line size, which is 64 bytes, and the passy is to calculate the hit ratio need to obtain an average access time of 20 ns. We need to use the following formula. Average access time equal to hit time plus miss rate multiplied by miss penalty. Given that the cache access time is 5 ns and the time to transfer the line to cache memory is 200 ns, we can substitute this value into the formula and solve for the miss rate. 20 ns equal to 5 ns plus miss rate multiplied by 100 on to 200 ns. So the result of miss rate is equal to 0.075 ns. The number of vector line is 6 kb multiplied by 6 division 6 6 64 64 b is same 1 1000 24. The number of direct step is 1024 multiplied division 2 equal 501 512. The number of line process to two-way associative. This is this table. We see task 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 is T equal 32. uh, 32 32 stress not check subtract equal 70 with index I equal look to what 5 with the 5 with now the save that with offset oh look to 60 is the equal 6 they have to look per week per week in the case of this equal the genetic the genetic uh, plus plus the this penalty is equal from is equal to and plus 100 20 and that's the same one 140 and that's
Here is the cost. Here is the type of cost according to the cost request here. The number of direct line is the 50 50 50 uh, 50 60 uh, say is the same uh, 2 million 2 million 48 the number of process process is 2 million 2 million 48 division 4 is the same 500 12 the number of line process is 4 so 4 way to uh, succeed succeed so that is half is the same t t uh, 50 50 52 52 uh, struck 9 struck 4 is the same 90 index look to 500 500 pound but it's equal 9 8 offset uh, offset is the same look to uh, 60 uh, equal 4 bit Chinese for Chinese one is for Chinese O Chinese 0 index is 0 address is 0 0 Chinese 2 second 2 is Chinese 0 index is 1 the number of the check Sanchez is 2 the number of Sanchez hit is 3 million 3 million 3 attracts 2 is 3 million 1 the hit radio 3 million 3 3 million 1 division 3 million 3 is 9 99.3%. That is to exercise 7. Um, uh, 32 50 32 bit computer has a data shared memory with FAD and line of 60 64 bit 64 byte calculate the bit radio of this program this program dot double double A one uh, 1 million 1 million 24 B one 1 million 24 C one 1 million 24 and B one million 24 double this X by X by the operates the consecutive bit for for is supposed the future use the flex map function and y back point police the different use the associative and structure with L or as the replacement out the general use two-way associative general functional and associative functional or with L or G as the replacement
And now move to the exercise 8. Case size equal 32 kilobyte, block size equal 64 byte. So number of block in case equal 32 kilobyte divided by 64 byte and equal 32 times 2 to the power of 10 divided by 64 equal 2 to the power of 9 and equal 512 blocks. Assume integer size is 4 bytes, so array M 512 size equal 2 to the power of 9 times 2 to the power of 9 times 4 equal 2 to the power of 20 byte and equal 2 to the power of 14 blocks. One block contains 64 bytes divided by 4 bytes equal 16 elements. Now consider the code segment. In the following code segment, here our matrix M is row measure stored by rows, and we read the row by row. So for one element we read a block, 16 elements. For one mismatch, 15 elements are hit. So hit ratio equal 2 to the power of 20 minus 2 to the power of 14 divided by 2 to the power of 18 equal 0.93. Now consider the following code segment. Here, our matrix is row measure and we reading column wise. As our case is two-way set associative and it had 512 blocks, so there are 512 divided by 2 equal 256 sets. So 0. 256 512 blocks are mapped to set 0. 1 to power 257 513 are mapped to set 1. Here each row has 512 elements and equal 128 blocks. As we read column wise, we read in following order: 0, 128, 256, 512. So we read an array M00 and load block 0 to set 0. Then M10 and load the block 128 to set 1. Then M20 to set 0. Now set 0 is full. Then we read M20 and load block 384 to set 1. Now set 1 is full. Then read M30 and load block 512 to set 0 and replace block 0 from cache. So as block 0 is replaced, to read other element in block 0, we have to bring block 0 again to cache. So for each element, we have one block read. So hit ratio equals 0. Now move to the exercise 9. Cache contain 64 byte chunks. Words equals 64 per line. There are 4 lines per set. So total number of words in one line equals 64. The cache is split up into 4 lines per one set. This is a 4-way associativity. In absence of cache, the memory access time will be calculated as 4352 times 10x equal 43 520x. Here x is considered as the time for one asset and the fetch sequence to repeat 9 more times, mean total 10 times. We have 64 words per line and 4 lines per set in the case. So total size is 40, 19 and 96 words. Hence the total of sets equal 40, 96 divided by 64 times 4 and equal 14 sets. After assessing 14 times 64 equal 1024 words from 0 to 1023 each and every set will be occupied with one entry as it has 4-way associativity. All sets will have 3 space more to occupy, so words will get filled from 0 to 14, 19, 90, 0 to 40, 95. In next iteration from 40, 96 to 41, 59. It means 40, 96 plus 1663. The cache line in the first set from 0 to 63 will get replaced because of RLRU for block replacement. So total number of cache line replacement will be 43, 51 minus 40, 96 divided by 64 and equal 4 replacement. Processor extract was starting from 0 and ending to 43, 51 location. As next, the starting 4 cache line approach will be missed due to the reason that they are replaced. The cache line will replace the old one in the set. For line 0 to 63, will replace 10, 24 to 10, 95. Line 10, 24, 10 to 10, 193 will replace 20, 48 to 21, 11, and similarly all new line approach will be missed, so we will have 16 line missed for each from the starting 4 sets. No line of cache will be missed for the 5th set to 16 sets. Hence, for the line 40, 96 to the 43, 51, 4 lines of cache will be missed which are from the first 4 sets. Hence, in total, 16 lines that were missed and last 4 lines missed equal 20 lines of cache missed. So in present of case, the memory access time will be calculated as total number of memory access time hit time number of cache line missed time memory access time for a line and equal 43, 52 times 10 times 0.1x plus 68 plus 9 times 20 times 64x and equal 20, 20 and equal 20, 224x. Here X is considered as a time for one memory asset and the cache is 10 times faster than main memory. Therefore, 0.1x and here 68 cache line will be replaced as X new cache line asset replace the subsequent to be asset but key for LRU and hence performance improvement equal 43 528 divided by 20 224x. Now move to the exercise 10. The visual address format for a computer with visual address of 32 bits and page of 2 kilobytes is as follows. The first 20 bits are used to represent the page number. The remaining 12 bits are used to represent the offset within the page. The maximum number of pages in this computer is calculated as follows. The size of the visual address space is 2 to the power of 32 bytes. The size of each page is 2 to the power of 11 bytes. Uh, Therefore, the maximum number of pages in this computer is 2 to the power of 32 divided by 2 to the power of 11 and equal 2 to the power of 21 and equal 20 97 152 page.
Okay, hello everyone. My name is Nguyễn Quang Minh. I'm a member from the group 4 from the class B4. My student ID is 13PI13299. So today I'm going to talk about the exercise about chapter 5 memory hierarchy. I'm gonna do exercise 11, 12 and 13. So first we begin with the exercise 11. So in the question A of the 11 exercise 11, the virtual address format will depend on the given information. In this case, we have a computer with a memory address of 20 bit and virtual memory with page of 1 kilobyte. First, to determine the virtual address format, we need to consider the size of the virtual address space. Since the computer has a memory address of 20 bit, the virtual address space can be calculated as 2 to 20, which is about 1,048,576 address. The page size of given as 1 kilobyte, which is equivalent to 10 bytes. So page we have to 10 byte address. Therefore, the virtual address format will consist of two field page number. This field will have enough bit to represent the total number of the page in the virtual address space. In this case, the virtual address space is 220, and since each page has 210 address, the page number field will require 10 bit. Offset. This field will have enough bit to represent the offset within a page. Since each page is 1 kilobyte, the offset field will require 10 bit. So the virtual address format will be as follows: page number and the offset. Next, we move to the B question to determine the number of entry. In page number, we need to consider the number of the page in the virtual address space. As calculated above, the virtual address space has 220 address, and each page is 1 kilobyte. We have the function that the number of entry in the page table equal to the virtual address by divide page of page size number of entry in the page number of the page table equal to 1.024 entries. Therefore, the page the table in one level will have 1024 entries. In the C question, the main memory of has a capacity of 256 kilobyte and the page size is 1 kilobyte. To determine the number of the frame in the memory, we need to divide the memory capacity by the page size. We will have the function that number of frame in the memory equal to the memory capacity divided page size number of frame in the main memory equal to 256 frames. So the main memory has 256 frames. With the D question, the field included in the page table typically include page number. This field stores the page number corresponding to the virtual address. Second is the frame number. This field stores the frame number in the memory where the corresponding page is stored. Third is valid and invalid bit. This bit indicates whether the page is valid or invalid. If it is set to valid, it means that corresponding page is currently in the main memory, and the opposite, that it means the page is not currently in the memories. Fourth, the protection set right. This field specifies the set right or permission for the page, such as read only, read write, execute, and more. Another function. It has enforcing memory protection and security. And finally, the control bit. The page table may include in addition control bit for various purposes, such as 30 bit to indicate if page has been modified, reference bit to check if the page has been accessed, and more. So the specified uses and structure of the field may vary depending on the memory management scheme and hardware architecture of the computer system. Let's move to the exercise level 12. So to calculate the value, we need to using the following formulas. With the A question, virtual, we have that virtual memorized size equal to 2 times number of address bit, and with B question, number of page equal to virtual memorized size divided page size. C question is frame size equal to page size. D question, number of frame equal to main memory size divide frame size. E question, that number of bits to select entry in the page table log 2 of number of page. F question, number of entry in the page table equal to number of page. And you have the information, the given information that number of address bits equal to 16 bits, page size equal to 2 kilobyte, and main memory size equal to 8 kilobyte. And when we calculate, we will have the result of them. So the A question, the virtual memory size equal to 65,536 bytes. B question, that number of page equal to 32 page, The C question, frame size equal to 2 kilobyte. The D question, the number of frame equal to 4 frames. The E question is number of bits to select entry in the batch table equal to 5 bits. And the F question, that number of entry in the batch table equal to number of batch equal to 32 entries. So we will have a summary of them. You can see that on screen. And next we move to the exercise 13. So to determine the virtual address size, page number, and displacement of the given virtual address, we need to consider the page of size of 8 kilobyte. Number one, virtual address size. The virtual address size refers to the total number of bits in the virtual address. Since the address is given in hexadecimal, we can convert into binary to determine the number of bits. The hexadecimal address is equivalent to binary address. Counting the number of bits, we find the virtual address is 32 bits. Number two, page number. The page number is the portion of the virtual address that identifies the specific page in the virtual memory. To find the page number, we need to determine the bits dedicated to the page number since the page size is 8 kilobyte. We calculate the number of bits required to represent the page number. The formula is the number of bits for page number equal to log 2 of page size and equal to 13. From the 32-bit virtual address, the most significant 13-bit starting from the left will represent the page number. In the binary, this bit are 001, 001. And 3. The displacement. The displacement is the portion of the virtual address that represents the offset within the page. It indicates the position of the desired data within the page. Since the page is 8 kilobyte, the displacement will require 13 bits to present all possible offset within page from remaining 19 bits of the 32-bit virtual address. The less significant 13-bit will represent the displacement, and you guys can see in the binary speed are on screen. And we will have the summary of exercise, summary of the result of the exercise 13. Virtual address size is 32 bit. The page number and displacement is about 13 bit. Okay, thank you for listening my presentation.